Well, I think we'll get started. Good afternoon, everyone. Welcome to a Safer Sim research brief. Today we have Dr. Samiul Hasan from the University of Central Florida. Dr. Hasan, interest in urban data science, developing data-driven methods to understand urban dynamics in human modality and activity behavior, lifestyle choices, network congestion, emergency response, and land use patterns. Today, he'll be speaking to us about a SaferSim project called Assessing Crash Risks of Evacuation Traffic, a simulation-based approach. So, Dr. Hassan, please take it over.
Thank you. Thank you, Don. Good afternoon, everyone. Welcome to the SaferSim research briefing on the findings of the project Assessing Crash Risks of Evacuation Traffic, a simulation-based approach. My name is Samiul Hasan. I'm an assistant professor at the University of Central Florida and the principal investigator of this project. And I have with me Mr. Rizal Rahman, who worked as a graduate research assistant in this project. So the motivation of this project comes from the devastating impact of the recent hurricanes, Irma, Harvey, Michael, and Matthew, and that created a major concern for most of the coastal regions in the United States. For example, during Hurricane Irma, about 6.5 million Floridians were ordered to evacuate. And this evacuation caused significant traffic congestion on the many interstates in the state. And for example, I-75, I-95, Florida Turnpike were highly congested. And we also noticed that during that period, about 221 crashes occurred on I-75 between September 7 to September 9. And Hurricane Irma made its landfall in September 10. So it is very clear that not only ensuring efficient evacuation, it also becomes very important to ensure a safe evacuation of a large number of people. And it will become a major challenge for transportation agencies. So with that motivation, we came out with a plan, and our research objectives were basically to understand or assess the impact of hurricane evacuation on crash risk, and to identify if there is any significant changes in traffic flow, behavior, or driving behavior between evacuation and non-evacuation periods. And we also wanted to understand if there is any in-vehicle driving assistance systems can play a significant role during evacuation period. So with that three objectives, we collected several data sets, mainly from RITIS, which is Regional Integrated Transportation Information Systems. And we collected from RITIS incident data, which includes crash, weather-related incident, congestion, and other events, which may include disabled vehicle, road construction related delays. We also collected traffic data, which include speed, volume, and occupancy data. And we collected this data for both evacuation and non-evacuation period. Our non-evacuation period include August 1 to August 31st in 2017, and September 4 to September 9 was the evacuation period data. And to give you a background, that Hurricane Irma the landfall of Hurricane Irma was on September 10. So this is a snapshot of the data where we pinpoint every crash location along I-75, and for every crash location we identified a downstream and upstream MVDS detectors, and we created some features for each of those data, for example traffic flow, speed, and some other additional features that I will be able to discuss in the later part. And to give a data exploration, we always wanted to understand how this hurricane evacuation was evolving. So to give a perspective, from September 6, there was some evacuation order where it started to issuing from Key West in Miami in Florida. And we started to see some high amount of traffic flow starting from 6, 7, 8, and 9. And September 10 was the landfall day. Typically in a hurricane affected area or region, landfall day there was not much traffic. Many of the areas have curfew on the landfall day, so no one actually moves. So most of the evacuees, they use the previous day or the 2 or 3 days prior to the landfall day, they evacuated. So many of the evacuees will choose 7 or 8, or most, if some decided to evacuate late, they will probably choose September 9, but not many on the landfall day. And with that, we see the traffic and found that a very irregular traffic flow pattern from the sensor data. We also looked at the incident, and from those incidents, we collected the specific crashes that happened. So you see that on this, from September 9 to September 16, we plotted all individual number of crashes, and on particularly 3 days, as I just said, that not many people travel the day before the landfall and the landfall day, but they travel 2 or 3 or 4 days prior to the landfall. So September 6, 7, and 8, we see a significant increase in the number of crashes. So we can see there might be some correlation on the irregular traffic flow pattern and the increased number of crashes. And here you can see that the Hurricane Irma made its landfall on September 10 at 4 p.m. and it made its earlier landfall on the Key West on the same September 10. So now we created a data visualization tool to understand how evacuees are departing in different areas from different areas and how these crashes are progressing. So in this data visualization, you'll see as hurricane was progressing, as we are going very close to the landfall, we will have more and more number of crashes very close to the upstream, very close to the downstream, so up to the northern area, very close to the border of Georgia and Florida. Most of the people many of the people evacuated to Atlanta area. So you'll see that increased number of crashes, 6, 7, and 8, and along those I-75 corridor, we will have increased number of crashes near the border. So in this one, you will see that in the number of crashes will keep on increasing, and as we have more and more crashes, it will go along the border. And after that, after landfall, there will be less and less number of crashes. And when people are coming back, there could be some increased number of crashes, but that is much more dispersed. And we made this visualization very interactive, so you can actually zoom in to the places. So if you choose a particular date, for example, we choose here September 8th, and we can zoom in and find out, pinpoint every specific location, and that will aggregate the number of crashes along this segment, and that will find out specific type or characteristics of the crash. So this tool could be very useful to find out the aggregate number of crashes and visualize them along a specific corridor. So what we have just visualized, it happened over I-75. So with that, I would like to start with our analysis on evacuation crash risk assessment. So in this part, we'll basically look at two things. So what we collected data for evacuation period and non-evacuation period. So for non-evacuation period, we have 78 crashes, and for this approach, we actually use case control study. So where we collected both evacuation and non-evacuation data to understand how the likelihood of a crash changes during evacuation period and a non-evacuation period. For every crash, we have a crash precursor period of 5 to 10 minutes just before the crash, and we assume that the traffic recovers within 1 hour after the crash. And for non-evacuation period, we actually selected for every crash for M non-crashes. So this M can vary from 1 to 5, and we actually control for location, time of the day, and day of the week. For evacuation period, we have identified 63 crashes, and for choosing the non-crash data, we actually could control for day and location. We could not control for the day of the week for evacuation period, but evacuation just happened for 5 days. Now typically for evacuation data, this type of case control study, they use a model called conditional logistic regression. So we used the same model and we created some independent variables. So for example, in addition to speed, volume, and occupancy, we actually used standard deviation of speed and coefficient of variation of speed. And we compare our result with previous studies, and similar variables were identified significant of having the likelihood of a crash. So for example, regular period, both CVS and occupancy at upstream location has significant influence on crash occurrence. And in the evacuation period, we actually found that high variation of speed at the downstream location and high traffic volume at the upstream location. And you can see the upstream and downstream location on the right side of the figure, and increases the crash risk during evacuation. However, we are unable to compare these two results because regular period and evacuation period are coming from two different sample distribution, because our regular period consists of data for 1 month and evacuation period consists data of only 5 days. To overcome this issue, we actually combine all the samples of evacuation and non-evacuation period without any matching, and we actually used a new variable called EVC, which represent that whether an evacuation was occurring on that time period or not. So when we combine this data and run a simple logistic regression model, we use the same variable of volume and coefficient of variation at the downstream and volume at upstream, and use EVC just to indicate that an evacuation is occurring. And we found out that this evacuation variable came out significant and positive, which basically means that evacuation itself increases the likelihood of crash. Compared to regular period, if there is an evacuation going on, it actually increases the likelihood of a crash, which has significant implication. And I will discuss the implication of this result. So now, since we have identified with the combined data of modeling that with controlling for all the location, traffic, all the day of the week, time of the day, considering all those variables, we found out that evacuation can be have some significant role to play in the occurrence of crash. So in this part, we actually look at if we can identify it from the simulation, the micro simulation of the of those evacuees, and we try to see if we can also understand that if any in-vehicle system, driver assistance system, can play a role to reduce those crash risks. So what we did here is that we simulated in Sumo 9.5 miles long segment of I-75, which is not in the northbound direction between Ocala to Gainesville. And the study location is basically selected based on the previous crash occurrence. For example, the maximum number of crashes occurred in September 8 during this evacuation period between 2 p.m. to 5 p.m. So we selected the simulation experience from 1:30 p.m. to 3:30 p.m. and we developed the traffic network. We gave all the vehicle inputs and we gave all the routing inputs as well. And with that, what we did is that we see that we try to calibrate our simulation for an evacuation period. So we use some statistics that are available, GEH statistic and absolute speed difference, to see that how well our simulation was calibrated for evacuation period. And this is a significant milestone because previously all the simulators that have been used for evacuation data, they were not calibrated for evacuation, real world evacuation data. With so much data available for during Hurricane Irma and a real evacuation, we can actually calibrate a simulator, microscopic simulator for this type of data. So we found that for 72% of the data and 73% of the observation, we have the absolute speed difference less than 2.5 meters per second. We also see that we also measured the root mean square error and root mean square percentage error, and we found they're quite low for the volume and speed metric. So which establish that the simulator that we have calibrated, it is well calibrated for an evacuation period, and the calibration results can be used for future studies as well. So with that calibration, we've noticed that the higher values of maximum acceleration, for example, in 4.5 meter per second square, and this is higher compared to 3 meter per second square in typical situation, and higher deceleration value, 6.5 meter per second square compared to 5.5 meter per second square. So this indicates that abrupt speed variation during evacuation compared to a typical period, and this indicates that how different are the driving situation during evacuation period. So what we did is that we use this evacuation base condition. So we estimated a base condition of traffic simulation, and we see that how can we represent. So we estimate some proxy variables. So the proxy variables for potential collision risk is time to collision, TTC, and deceleration to avoid a collision, so DRSC values. So we measured those values, and we said that the potential collision risk will be TTC if TTC is less than 1.5 second and DRSC value greater than 3.35 meter per second square. And if you see in the two graph, we actually plotted all the distribution of those values, and we find out that there's a significant number of collision risk. And we are saying that this is potential collision risk because in simulation we cannot find actual collision. So this is more of like the risk of a collision, potential collision. And with that base condition, we actually measured that we use an ACC controller in those vehicles in the simulator. And this ACC controller, there in Sumo, there is a car following model for those ACC controller, and we choose different penetrations of 25% to 50% to 75% to 100%. We use different market penetration rate of ACC vehicles and see how it changes those potential collision risks. So this is the one for 25% market penetration rate. You can see that the distribution of TTC and distribution of DRSC values significantly improves. So what it means is that if you look at this figure, that if in the base condition we have 264 potential collisions, and then if you just use one headway, for example, greater than 1.2 second headway, the number of collisions significantly drops. And what we found is that we did this simulation 10 times and averaged the result over those 10 simulation runs. And even for just using 25% of ACC equipped vehicles, we can reduce 50% of their potential collisions. To give the specific numbers, in this table you'll see that in the base condition we have 264 potential collisions, but in the 25% market penetration rate we have around 131 potential collisions. So it's a significant drop, like we can drop 50%. And if you have higher penetration, we can drop significantly, but for higher penetration rate you have like 80%. You can drop 80% of the potential collision risk. Now one question that might come, that this might improve the safety situation, but what happens to the travel time? So we actually also measured the travel time, average travel time to cover the particular segment, and with these ACC vehicles we see that for 50%, 25% and 50%, the travel time actually drops. And if you use 75% to 100% market penetration rate, the travel time increases, but the increase is not that significant. So with that one, we actually can identify that how the ACC controller can help for understanding the risk of collisions during evacuation. And what we have identified is that our results can have some implications. So I would like to discuss some of the implications of these results. So for example, we can develop some crash prediction model. We have been developing crash prediction model in real time that can work on the regular period, but our result indicates that we can actually do this one in the evacuation period, and which could be a significant impact for the evacuees. We can adopt proactive measures such as warning evacuee drivers that there is a impending crash risk. We can also enforce drivers to reduce travel speed to a certain limit. So we can give some warning message through variable message signs. In addition, we can, for measuring some specific control situation, we can identify some crash locations, and based on those crash locations will be based on the prevailing traffic conditions during an evacuation. So these are some of the implications that we thought, but some other, in addition to those implications that are coming from our results, we have also found that since evacuation itself has an implication on the crash risk, we can think of adopting a phased declaration of evacuation orders so that to reduce the traffic surge. So many of the cases you really don't have to evacuate At the same time, evacuation order can be issued in a coordinated way so that the traffic surge is not significant, and that might also reduce the number of crashes. One of the very important implications of this research is that many of the times practitioners use traffic simulation model to indicate the network clearance time during evacuation. But what traffic car following model they are going to use is a huge impact on what result they are going to get. And we think that they should adjust these model parameters based on the evacuation traffic. So they should calibrate the models based on evacuation traffic. And another implication is that we find out that even within a modest 25% market penetration rate, and which is not very significant compared to the adaptive cruise control system, availability of adaptive cruise control systems, and we can reduce the number of crashes and improve the traffic condition during evacuation. So each of those crash will also increase the number of travel time and delay for the evacuees. And during evacuation, the delay is significant. To reach from one point to another point, which is typically 1 hour, it takes 3 to 4 hours to reach the same distance. So if you can reduce any kind of travel delay, that will have a huge impact on the efficiency of the evacuation also. However, we would like to say that this result is not field deployed. So we haven't tested based on field deployment. There could be many issues on the connectivity, and then adaptive cruise control system can be implemented in that system. So we need to see the connectivity issues, like could be another opportunities available with connected vehicles. So if we have connectivity between vehicles or connectivity between vehicles and infrastructure, the situation could be significantly improved. So we have used these research findings. So I personally shared these research findings with the Florida Department of Transportation, one engineer who is involved with overseeing the evacuation scenario for that department. We presented one paper in TRB annual meeting based on this research, and we have prepared 2 journal papers. One is about the crash risk assessment, and another one is how to reduce the number of crashes using these adaptive cruise control technologies. And with that, I would like to thank SaferSim for funding this research at UCF. I would like to thank Dr. Mohammed Ati, Naveen Eluru, Mohammed Zaki, Ching Kai, and Ina Wu for helping at different stages of this research. At SaferSim, I'd like to thank Don Marshall and Jacob Hayden for overseeing this project. And thank you all for listening to my talk. If you have any question, you can contact me at this email address, but I will be happy to answer if you have any.
Can you tell me a little bit about that context, like what they were interested in, what they might do with these results?
So one contact is in the headquarters in Tallahassee. So he oversees all the studies related to hurricane evacuation and how traffic system management and operations and safety related issues. And I basically shared with him that we wrote 2 papers out of it, the draft versions. So and then we talked about another person who is in District 5 Central, who manages some of the interstate, for example, I-75 and I-4 and I-95 sections. So he oversees the evacuation related problems. So there are some different agencies involved there, and Florida Department of Transportation sits in some of those places. So I talked with him about the findings, how we can improve it, and the evacuation scenario and what observations we have found. And he says that there could be some potential to share this result in their different meetings that they have. So they organize meetings periodically to share it in a broader agency. So there are many agencies involved managing disaster, for example, emergency management agencies and different transportation, Central Florida Expressway Authority, Florida Turnpike Authority, and as well as some local agencies that they give evacuation orders as well. So I'm hoping to present these findings to one of those meetings. So that we could not have an opportunity to share the specifics of what part they think is valuable, what part they don't think is valuable. But once I share that result in a specific setting, I might get some more pointed feedback.
Okay, I'm just very interested because it's interesting results, and I know you just said you can't share what they thought was interesting, but it would be enlightening to see how they take these results and then implement changes in policies or the way they manage evacuations because of these results. That's why I was curious. Um,
Yes, sure. Yeah.
Have you said, could you go back one slide to your papers? Is that one or two slides back?
These are the papers you mean this slide?
Yeah. I just wanted to take note of those and to let people who will be viewing the video later have a chance to take notes of those because I think those would be so probably more information in those papers than is available in this webinar. So
Yes, we had one we had one conference paper, but unfortunately those papers are no longer available in the proceedings.
okay.
Uh, because TRB doesn't let this, but we have these two papers in the draft version, so we're going to submit in very soon. So hopefully they will be. If you have any preprint server, we can put it in the preprint server.
Okay. And so if someone wants to receive a copy of those papers, I assume they can contact you, and then if they're shareable, you can send that.
Yes, sure.
And then I also want to
Yes.
mention that your project report is also on the Safersym website.
Yes, our project report is available. So that project report has most of the findings that we have, and then we have one additional after we finish, and this we have some. If we have some further analysis, we'll be able to include those in the papers. So the papers will be like the response to the comments and those things. So the report will be the first place to look at, and if they have some additional questions or additional information to look at, they can ask and we can share the draft of those papers.
Thank you very much. I just wanted to make sure people caught those papers. So I don't have any other questions. I appreciate the well-paced presentation you gave. Thank you very much.
Thank you.
I don't see any questions coming up in the chat, so I think we are ready to close.
I have one. There is one question.
Oh, yes.
Oh no, there is no question. Somebody says. Thank you.
Okay. Well, thank you for presenting, and thank you to the attendees. And I expect we'll have a lot more people also watching on the YouTube channel when the video is posted. We see a lot of people going there.
Oh, okay.
So we'll watch the comments.